Dear all, my warm welcome. I'm Lakmal from Civil Engineering Department, University of Peradeniya. I'm delighted to present in this conference my research work entitled Finite Element Stress-Based Analysis on Progressive Valley of Kahagalla Landslide. My talk is organized in the following steps: introduction, objective, geology, methodology, data integration, modeling and boundary condition analysis, discussion, conclusion, and references. Let me start by saying a few words about the site background. Landslides are a natural process that plays a key role in landscape evolution of mountains and hilly environments, especially in central highlands in Sri Lanka, which are categorized by a steep slope, deep gorge, frequent fold, escarpment, highly weathered slope, intensive and prolonged rainfall. These are favorable for the occurrence of slope movements after rainy season in most part of the Central Highlands. In 1987, rainfall triggered Kahagalla landslide, causing considerable damage to Peradeniya Harlier Road, blocking the carriages for a period of over 5 weeks and leaving occasional road subsidence following rains. The objectives of this presentation are to provide an interpretation of landslide failure mechanism, to determine the slip surface location, to interpret the combination between rainfall and the landslide activation. For that purpose, numerical model developed to investigate the mode of retrogressive behavior of the saturated sliding mass at Kahagalla landslide. It is located at an elevation of 1,430 meters above Messel in the area around 16 road, covering 3.5 hectares on the western slope of the mountain range, running northeast from up the lake. I would like to show the major slip boundaries identified and the plan view of the landslide. Many localized failures, extension cracks were observed near the A16 road, embankment indicating that the entire mass was moving towards the village located nearby Lower Hill Slope. Kahagalla landslide activates in the wet season of the Central Highlands and damages to the A16 road. As an illustration, I have added photographs which has been taken after prolonged precipitation during the month of December 2014. Landslide features identify over the landslide body is shown in the photographs and the key map. Escarpments, water springs, ponds, open cracks can be seen, and there is no well-defined drainage system. The slope of the hammock ground are flatter, and the depressions are filled with sand and mud and water. Topology of the earth strip is categorized by hammocky surface terrain. The general geology of study site is categorized by calc gneiss, charnocite gneiss, garnet, biotite type, and condylite. The material within the site area consists of polyval deposits and acid weathered residual material. The site is dominated by sandy silt and city sand, white gravel, and rock boulders are distributed in an irregular way. The scar area of this slip has subsided during the sinking into solution cavities of the calc gneiss underneath, and the presence of solution cavities were detected during the drilling. The present work literature review, fieldwork, laboratory test, instrumentation, finite element method, together with limited method are employed for the methodology. My methodology is interpreting the available data, site model, finite element, stress-based analysis, and finally verify the failure mechanism. Sigma W and SOAP W of GeoStudio package used for the finite element and equilibrium method analysis. Now I'm going to present the available investigation data and instrumentation data I use for the current study. This research is based on the investigation and monitoring data obtained for the landslide disaster protection project and the NBRO report prepared for the ADB funded second road improvement project in 1989. The boreholes were drilled to the bedrock to establish the stratigraphy and for the purpose of landslide instrumentation. 3 inclinometers to pipes and gauges, 3 water level meters installed in these boreholes. In addition, coextensometers installed across the right boundaries to observe the surface movements as shown in the plan. In order to determine the most appropriate cohesion value for back analysis, direct shear tests were carried out for the undisturbed samples taken at the site boundaries to determine the most appropriate value of cohesion for the back analysis of factor of safety. Justice has reviewed that the cohesion can be set to 0 for back calculation of factor of safety. Slip surface location and parameter values were determined using core samples, borehole logs, instrumentation data, rainfall data, and direct shear tests are carried out for UD samples. You can see the investigation layout shown in the contour map. There are 8 boreholes investigated by NPR in 1987 and 10 boreholes including instrument under LPP. Bending of pipes in inclinometer locations and pipe strain gauge locations observed during the rainfall and location of the slip surface confirmed. It is in that the slip surface in most of the locations commonly displaced nearby bedrock with bedrock interface. Water losses observed during the drilling and slip material encountered at the same level. You can see the slip surface name SPO and another 2 locations identified below SPO. S3 slip surface identified and another slip surface identified below S3, and S2 slip surface identified and another slip surface identified below S1. S1 slip surface identified is a major slip surface of this landslide. Let me elaborate further on the slip surface identification and the landslide block divisions. Kahagalla landslide recognized 4 landslide blocks A, B, C, D, and their respective slip surface identified here as S4, S3, S2, and S1. S1 is the largest SIP surface which is identified as a major failure, and the other SIP surfaces are located above the top S1. Let's now look at the next slide, which shows the landslide movement observation through extensive data and rainfall. If you look at this graph, you can see that how the landslide movements against rainfall. I would like to illustrate this point by showing you the investigation plan again. Figure 5 illustrates the surface displacements of the extensometers and rainfall data at the landslide. We see that can be seen the E4 responds early to the surface variation with a higher rate of displacement during the rainfall than the others. E4 is located at the left flank of the landslide closer to the S4. Based on the figure 5, it seems S4 activates early before the initiation of movement at the other SIP surfaces, showing retrogressive behavior. It was experienced that the groundwater level reading B9 also has gradually increased up to a steady level. Let's move to the next slide. Location of the periodic surface. Periodic surface has continuously been recorded using a groundwater level monitoring boreholes and carrying out stability analysis on this SIP surface. Critical water level that has refers to the groundwater level that is highly susceptible to initiate the landslide during rainfall is considered for this research. This activation has been detected at the time the surface cracks appeared, supplemented by instrument indications. Boundary conditions used for the finite element analysis are fixed along the vertical right-hand side boundary and fixed xy along the bottom boundary. As in calculating stresses for a slope stability problem, the boundary for the base is selected as fixed xy, and the displacement in both x and y direction is not allowed at the base. 2D analysis is performed based on the LEM using slope W and FPM using sigma W of the studio package. Morgenstern price method was used for conducting back analysis of the landslide. The stability comprised with FPM stress-based back calculations is the instrumentation data reveal the order of activation of SIP services sliding mechanism needed to be identified. For that purpose, the factor of safety of each individual SIP surface was calculated by varying the friction angle from 14 degree to 80 degree with 0.25 decrement while keeping the soil cohesion to 0, so that the friction angle which gives a factor of safety value of unity can be assessed. Material parameters used in this analysis are shown in the table 3. You can see the stability results for the SIP surface S1 and S2. Likewise, I have analysis for S3 and S4, and the results are shown. All the results of the stability analysis for varied friction angle between 14 to 8 it's summarized in the table 4. Let me use a graphic to explain the results of the model analysis. You can see the variation of the factor of safety with the variation of the friction angle at critical water level. I think the graph perfectly shows that the S4 appears to be initiating earlier than the other SIP surfaces can be found to be initiating in the order of S1, S2, and S3. Also, it is significant that both S3 and S1 activates at the same time when the friction angle becomes approximately 10. The above analysis can be further extended by incorporating the unloading of the tow due to the activation of the SIP surface S4. Two scenarios are considered in this analysis. Case number 1, consider the SIP surface S4 has activated, thereby considering the removal of the tow support in assessing the stability of S1, S2, and S3. These are shown in the table number 5. Likewise, under the case number 2, consider the SIP surface S4 and S3 activated, thereby consider the removal of the tow support in assessing the stability of S1 and S2. Results are shown in the table number 6. Let's now turn to the discussion. The results indicating that the lower block bounded by S4 is activating initially, which is the critical factor of safety as compared with the other SIP surfaces. Also, it is significant that there is no much difference between the factor of safety values of the other failure surfaces at the time of S4 become unstable. With the failure occurred in S4, the modified slope becomes unstable again due to the loss of tow support, and S1 appears to the next slip surface where the failure would initiate exhibiting the characteristic of retrogressive type of slope failure. The soil masses bounded by S2 and S3, which are part of soil mass bounded by S1, would immediately become unstable. We see that the factor of safety of each slip surface has significantly reduced due to the tow unloading, causing the slope to become unstable. However, the stability analysis of S4 shows a factor of safety unity at a higher value of friction angle compared to the others. It is revealed that the S4 played a dominant role for the global slope stability of Kahagalla landslide. The block mass bounded by S4 provides lateral support to the blocks above it. By examining the value of factor of safety of SIP surfaces, can be deduced that the activation of SIP surfaces can be take place in a retrogressive manner. As a factor of safety of SIP surfaces, uphill of the S4 reduces to value that indicates the possibility of failure. According to the instrumentation data as well, failure has initiated in the slip surface S4 followed by failure along S1, S2, and S3. This leads to next point, which is conclusion of this research. I'd like to conclude by drawing your attention to my main point. Failure at this site propagates backwards and takes place at different times. The entire landslide area of this site moves intermittently during rainy season, leading block S4 at the top was the first slip surface to activate. Weighing at pros and cons, I come to a conclusion that mechanism of landslide at Kahagalla is of retrogressive type. And here my references. That brings me to the end of my presentation. Thank you for listening.